some of you will know that I did my PhD with Bob Parr, and this was on the wall of his lab, basically, was that we should be focusing on the discussion rather than the numbers. I'm going to definitely do that here, but I will show you numbers at the very end, just so the chemists don't fall asleep, right? There will be a few numbers at the end. But in the light of having discussion, certainly interrupt me, right? Do not hesitate. Oops. The same thing was happening yesterday. And okay. So I'm going to set up this setting. For everyone who heard my seminar on last week, you have permission to fall asleep for approximately 10 minutes while I set up my notation, okay? So this is our Schrodinger equation. Typically, because we're interested in elementary particles, it's going to stop here. But if we were interested in nucleons, we would want to take another couple terms potentially, right? I'm going to consider a fully generic one-body operator, so I could treat some sort of two-component relativity if I wanted to, right? So it's not going to matter. And the reason this is hard is because we need really incredible accuracy, something like 6 digits of precision or something like that, right? And so we need really good solutions to this problem. And the dimensionality of this problem is hard. So even though this is, some sort of innocent-looking, linear second-order partial differential equation, it's not an easy one, right? Okay, so I'm going to set up my notation. I have some 1-electron Hilbert space plus spin, right? And normally for me, spin is just plus or minus a half. If you like nuclei, you'd have spin and isospin. If you like qubits, you'd have 2 choices. Like it's just some sort of extra variable there. I'm not going to deal with what it is. And then the Fock space is the direct sum of the 0 particle space, 1 particle space, 2 particle, 3 particle, and so on. And we already saw this yesterday, Lorenzo and Natalia. You can do this for antisymmetric or symmetric spaces, right? You can take the antisymmetric or symmetric subspaces. That's going to be important because I'm going to use second quantization unlike them, and that's going to change what I'm doing a slight bit relative to yesterday. I think almost unnoticeably, but nonetheless, you should be aware, right? And so in second quantization, I'm going to choose a finite basis, and there's already a warning that there's certain special things that happen only in the infinite basis limit. I think it's really well known in DFT. Like DFT is sort of really innocent. Well, depending on how you think about it. It's either very innocent or exactly the opposite of very innocent in a finite basis set, right? But it's very different from what happens in the full space, right? And the same thing will be true, in fact, for density matrices, right? But we're going to do finite basis set. We have something that creates a single particle space. And then if we would create another particle on top of that, then we'll either symmetrize it or anti-symmetrize it, depending on whether they're bosons or fermions, right? So this is just notation. Then the adjoint of the creation is the removal. And then all of our statistics are encoded by these. The top sign is for bosons. The bottom sign is for fermions. And when I gave the long talk, I talked about anyons, right? But that's not important for this, right? So the statistics is all coded inside here. And then this is my state. So this is my basis set. I choose this basis set because I like it, right? And so the idea is I can create in some states, and I'm just choosing the obvious notation. If I raise something to the 0th power, it's multiplied by 1, right? If I add something to the 1st power, then that's create a particle in this state. If you're doing with fermions, you can either not create or create. If you have hardcore bosons, you can not create or create. If you have normal bosons, you could create this state multiple times if you wanted to, right? All fine, right? And these are either determinants or permanents, depending on whether you have bosons or fermions. This is just the basis I choose, right? It's really nice for fermions and hardcore bosons. It's just a bit string. That's the way we would code it, right? I think Peter was one of the very first people to code it that way. And if the sum of these occupation numbers is equal to the number of particles, then that's telling me that is the number of particles. So it's encoded in this. It's just the L1 norm of this bit string vector, right? And now I just take a linear combination of this basis, and that gives me a space. In general, a state in Fock space, right? But if everything in the sum had the same number of particles, then that would be now a state in Hilbert space, right? In just the in-electron Hilbert space, right? And when you build these states, you have this restriction. Of course, they're normalized, right? And I think, in some sense, that's the motivation for, instead of using the wave function, using the density matrix, right? Which we expand in our same basis, right? And the nice thing about this, just, it's Hermitian, has trace 1, it's positive semi-definite. The nice thing about that is now this is a nice convex set, right? And then if I would just restrict this to cases where the basis sets are all and the number of particles I care about, then that would be in particle density matrices, right? So then I'd be restricting myself to a certain particle number as opposed to just a generic density matrix in a Fock space, right? Okay. So now I need to define what I mean by a reduced density matrix. And a reduced density matrix I'm going to define as just the projection of my big density matrix onto a smaller set. And this is just a way of projecting onto a smaller set. I expand it in terms of my annihilation and creation operators, and that gives me, in this case, a k-body density matrix. And from this definition follows this specific normalization convention. There are different normalization conventions. The math people here are all using this normalized to 1, which is fine, right? Eugene used this without the k factorial in the denominator, basically, so just the distinguishable particles. That's also fine. Doesn't matter, just know what you're doing, right? And this reduced density matrix is just the partial trace of the full in-electron density matrix with a normalization factor. And it should be said that these normalization factors are really important that you restricted to the in-particle state. So these are wrong if you did not restrict yourself to the in-particle space at the beginning, right? And just to motivate this for the mathematicians who would like this to be trace 1, this is really tied to the fact that we think of these as these are identical particles. And it's not fair to just trace out over the last n-1 of them. You should sum over all the possible symmetric ways of doing it. Yeah.
You're saying it because the big gun that you take, which is the density matrix, you take it over the whole Fock space, right?
This here, in general, it would be over the whole Fock space, right? So I'm not restricting to a specific n-electron Fock space, in which case these things are no longer, I mean, we can define this with a partial trace, but we need to be careful. It will not satisfy this normalization convention if it's over the whole Fock space. And with the exception of for the 1 electron case, it does. So 1 electron, you can't see it, but just imagine if I gave you a 10 electron state and a 12 electron state, one would be normalized, let's say for the 2 electron, one would be normalized to 10 choose 2, one would be normalized to 12 choose 2, and if I average those 2 states, that's not 11 choose 2. Right? So you have to be careful. Yeah, the number operator is a symmetry, and I impose it, right? Because otherwise these things, unfortunately, sometimes you can't, right? Because the 1 matrix doesn't see it. So that's the reason there's a subtlety here, is for the 1 matrix. The same thing happens in DFT, is you can only force an expectation value. To force the eigenvalue, you need to be able to impose n squared, and that requires at least a 2 matrix, right? So because we can only impose the expectation value, we have to sort of be aware that we might be creating some injustice along the way, right? That's where it comes from, yeah.
Well, in principle, we could also have pair density matrix that break particle numbers, correct?
Yeah, of course, yeah. right? So I've introduced the density, these reduced densities, and there's these reduced density matrices, and now we can start to think about functionals. So we normally work up here. We work in the n-electron states. Like this would be wave function theory, if you like. And I've done a color coding here. The diagonal elements of these density matrices are what we would call the densities, right? Or the electron distribution functions, right? So this is density functional theory, right? And there's a intractable exact functional, right? We know how to write it down, but it's not possible to evaluate it, so we are just sort of stuck trying to approximate it, right? Eugene was talking about this side, right? So here, the functional is exactly known, but there's an unrepresentability problem we have, right? And so these are also painful. Very few people in this audience would remember this, but early in my career, in a totally misguided attempt, I tried working on this thing where there were no functionals and unrepresentability problems. And I don't know why I did that in retrospect. That was a very bad idea, but I think I didn't understand it in the front, right? So definitely don't go here. The argument for the one electron density matrix theory is it's better than density functional theory in the sense our descriptor is richer, but the unrepresentability problem hasn't kicked in yet, right? So in some sense, it has a flavor of maybe something for nothing, right? The descriptor isn't really much more complicated than the electron density, especially in the Kohn-Sham piece where you already have a density matrix. And you haven't run into the unrepresentability problem yet, right? So that's sort of the motivation. I would argue that, you can argue that you would like to, one of these two theories, a few people in the audience know I've suffered with this one also, right? So you could say that my career has been I suffered here, I suffered here, I suffered here, so now I'm going to suffer there, okay? This is the theme of...
Can I ask a question about the intractable exact functional?
Yeah.
Does it have some enormous symmetry properties? I mean, somehow, if it's intractable, it should also have some very good properties. And the question is, if you list all the good properties and maybe skip one or two, you get other functionals with almost as good properties. I mean, I'm saying, look at it from a property point of view.
So the standard approach in DFT that has been, so the program of research in DFT since, Hardy would know better than me, I'm going to say mid-1980s, okay? Has been to write down properties, constraints on the exact functional, and then try to build approximations that satisfy as many of them as possible, or empirically fit the data. So think of it as machine learning without neural networks. Now they use neural networks, but just it was, come up with your neural network, basically. Machine learning with this neural network, basically, right? And I'm not, enormous success, right? But maybe not as much success recently as in the past, right? You sort of saturate at some point. Hardy?
There's one side remark in response to your question. So there are many exact properties, but their importance is very different. Some are very important. If you violate them, the resulting functional is a disaster. There are others that are not so important. And I think today one does not have a single function L that satisfies all exact properties that are known. Very hard to do. But the art is to know which are the important ones and to satisfy those.
Yeah.
Thanks a lot.
Yeah, so in fact, one of the earliest functionals dating from the 1990s when I was a beginning graduate student was the Wilson-Levy functional, which satisfied more exact properties than anything else by probably a factor of 2, right? And it was not very good. Right? So it just sort of, so anyway, it's an art, okay? DFT is an art. Given that this is also a functional problem, I'm going to guess it's also an art, right? Yeah. Particle hole duality. So this actually has the same unrepresentability conditions as this, because this is the one hole density matrix. So there's a paper from Carson and Keller in like the 1970s on this, right? So yeah, turns out, but of course, so that's why I said these are intractable descriptors, just because the number of variables in these descriptors is killing you, even though now the unrepresentability has somehow gotten easier. You could argue that the unrepresentability problem peaks sort of like at n over 2, right? Because there's just symmetry, particle hole symmetry. After that, it starts getting easier again. Okay? So this is my Hamiltonian. It's got a one-body part and a two-body part, and I'm not going to worry about the rest of this. And this is just to help the optimal transport people. So this is the way we're going to write it. We've expanded it in our anti-symmetric state. So yesterday, Lorenzo did this, and he wrote his Hamiltonian in the full Fock space, and then he projected later, right? We project at the very beginning because it's easy with our notation, right? And then this is just the notation that you would think of as this is a one electron operator, and then on a two electron space, you could act on the first electron or act on the second electron. And the two electron operator, again, you could act on a two electron space, and in the three electron space, you act on any choice of the two electrons, right? The main thing, and it's really not going to affect what we do very much, is that the operators already have the anti-symmetry in them. We don't have to do a projection at the end, right? So our basis will have anti-symmetry in it, and our operators will have anti-symmetry in them. It just makes everything easy. We're working fully within the anti-symmetric subspace the whole time. Okay? So this is a long slide, and it's cut off at the end, but that's okay. We'll make that work. And we're just going to walk through it really methodically, okay? This is the variational principle for energy, right? So we have the Hamiltonian, we have the in-electron density matrix. Here I forced, this is really density matrices that have exactly in electrons in them, right? So these are eigenstates of the particle number operator. And this is exactly the in-electron ground state energy, right? And that's an upper bound to what would happen if you only force the expectation value of the in-electron energy to be correct, right? And it's a strict upper bound, right? There are exceptions known, right?
Short question.
Yeah.
If I have a ground, I mean, if I look for the ground state of H, it's always, and if H commutes to the number operator,
Yeah.
then the ground state is always the vector state with exactly in particles, right?
So there are states with exactly in particles, but you can't rule out that they're symmetry breaking states. So the lowest energy state, once you go to states that only have an expectation number of n particles, it could be that, so let me think of it as a chemist. If I gave you two state systems and they both had 10 electrons, it might be that they would spontaneously like to become one system with 9 electrons and one system with 11 electrons, right? Yeah, I agree.
Because of that.
And so it has eigenfunctions of the number operator, yes.
But you could have an eigenvector. You could have two eigenvectors with different eigenvalues of the number operator and the same eigenvalue for the Hamiltonian. And the mixture of them would still be a ground state.
Right. But the main thing is, we no longer, there's no eigen problem here, right? This is just a minimum energy problem, right?
Okay, but then it's it's actually equality, right? Still.
Only in special cases is it equality.
You don't know that the
energy isn't convex in number of particles. If the energy isn't convex in number of particles, right?
Okay, maybe I come back.
No, but the true minimum.
I think I don't get it.
It could be that the true minimum of the energy is achieved with 3 electrons and 5 electrons. And then the average of the two states will give you the expected value of 4 electrons.
Right, but let's
It's not an eigenfunction, right? But there's nothing about eigenfunctions here. It's just variational.
Is it strictly speaking because you allowed minimizing set now become bigger?
Minimizing
that's why
bigger. Here it had to be an eigenfunction number of particles. Now I just say the
any
expectation value of
possible
number of
number of
particles.
particles, just an expectation.
Right.
Yeah, that's why it's.
That's it. Right.
Just a question.
Yep.
From a chemistry point of view, isn't this more natural because you never have a single molecule? Maybe there's more than one, so they will.
Yeah, and this is the zero temperature limit of this also. Right.
Yes.
So in practice, in a chemical point of view, this is more natural. We should always be thinking about mixed states because this is what we do, right? We always have some temperature, right? Right. This is really a fine point. Like the chances this bothers you is basically zero, we hope, right? So now we had our Hamiltonian. It has a one-body piece and a two-body piece, but the one-body piece we can evaluate with just the one-body density matrix. And the two-body piece, now we're going to evaluate with the full density matrix. Now we could have used just the two-body density matrix, but I'm depressed about the two-body density matrix and the unrepresentability, right? So we're going to keep this here. And here's the one-body piece, and then this is falling off the end of the slide, but that's fortunate because the next slide has it here. Okay, so this is where we had gone through. We formed our lower bound. Then I have this, what I'm calling the Levy-Valone functional, right? Comes from these papers right around 1980. And this Levy-Valone functional is exactly just minimizing the, if you like, the two-body operator subject to the constraint that the n-electron density matrix gives the right one-electron density matrix. So I broke my minimum into two pieces. First, minimize over all the n-particle states that give me the right one matrix, and then minimize over one matrices that satisfy the right constraints, right? Which are basically that it has the right trace, it's Hermitian, and the spectrum is between 0 and 1, right? So again, this is, strongly linked to the sort of things that Halle and Lorenzo were talking about, just slight things like my normalization is different, right?
Well, is it correct to say that this is the same as Levy-Lieb, but for density matrix?
Yeah, this is the same as Levy-Lieb, but for density matrix, right? So if we, instead of this, we had said gamma giving rho, right? Then this would be the density functional and the, yeah. It's actually Levy-Valone, right? Because Valone came up with this before Lieb, but yes. Okay. So this sort of motivates, if you like, the idea of why don't we really use this as our fundamental descriptor? And I'm sort of not doing this in chronological order, but 5 years before these functionals, Gilbert proved this existence theorem, right? Which is the direct analog of the Hohenberg-Kohn theorem for density functional theory, but for density matrices. And the proof is exactly the same, right? There's no insight in this proof, right? There's some subtleties, which are the same subtleties that exist in DFT, but we usually don't think about them in DFT, which is that given a density matrix on the interior of the unrepresentable region, there's at most one electron Hamiltonian, right? Yep.
Is it for finite or infinite? For which dimensionality?
It doesn't matter in this case.
Doesn't matter.
It doesn't matter in this case, right? So this is a theorem that's solid no matter what, right? It is, well, with the following caveats, right? I've already gotten rid of magnetic fields because that's evil in DFT, it's evil here. This would be like a constant shift in the potential. This is a constant shift in the one-body operator. We consider these the same operator, right? And it's really important that it's on the interior. If you're on the boundary, it doesn't work, right?
Is it an existence or uniqueness for example?
So,
is it both?
no, it doesn't. So, okay, in finite dimensions, every H has a ground state gamma, one or more,
Yeah,
right?
This is what they refer to.
Right? in infinite dimensions, there are certainly H's that do not have any gamma, right? So they have no bound state, right? So it's that this is at most 1, right? So it could have 0, right? Right? But it can't have 2, right? That's the only thing.
Sorry, I didn't get it. So in finite dimension, you actually don't have uniqueness, but in infinite dimension, you have always uniqueness, but not necessarily existence. I'm confused about it.
Okay, so in finite dimension,
Yeah.
if you give me a gamma,
Right.
it will come from AH, right?
It's uniquely? No.
Uniquely. There is one and only one H,
Okay.
right? Yeah.
I don't think that's true because in finite dimensions, if we have, for instance, the tendency actually, we can have peaks in the functional, and then different one-particle Hamiltonians would give you the same ground state one idea in the case of the degenerate ground state.
In the case of a degenerate ground state, I would say that you would have multiple 1 RDMs for the same H,
Yes.
but not multiple H's for the same 1 RDM.
Yeah, but you suppose you have a functional which has like a kink vector. You can choose your normal vector of the one-particle Hamiltonian. You can.
Oh yeah, I understand what you're saying. You're saying if you have a kink, then there may be more than one subgradient, basically, right? So this would correspond, yeah, so this corresponds, I think, based on my understanding of the Gilbert proof, this should correspond to something on your boundary. So I can't think of one that wouldn't be on your boundary. Okay, so if so, there's something wrong with the Gilbert proof. So I would be curious what it is. So, yeah, it's for non-degenerate ground states. So for degenerate ground states, your result is more subtle. I agree with that, right? So for degenerate ground states, there's a more subtle result. It's true in DFT too. It's more subtle, but it basically still works, right? So yeah, I should clean that up. In fact, this is sort of the fundamental results, and this is true no matter what. This is the true, this is the way you prove it for degenerate ground states in DFT too, is you have this swapping condition where if you have some sets of H's and their gammas, if you rearrange them in any order, you permute them, the energy always goes up. And this is the basic thing, and this is all you need in order to prove that that if you give me a gamma, I can find exactly the H that goes with it. Okay. So this now gives me this variational principle. For degenerate states, the argument is clearly not unique, right? It's concave in H, and it's, well, convex in N by definition, by the way the functional is set up, right? Right? The equality is only when the exact energy is also convex in N, right? So if the exact energy is not convex in N, then we have this thing that we had with this discussion before, where you have symmetry breaking in particle number. Okay? So here's the dual functional. This is something that I worked on, 20 years ago now. It's trivial. This is exactly the same as the Legendre transfer functional in DFT, right? So the proof of this is one line, if you like. This is a convex function, right? You cannot replace your supremum with the maximum. This goes back to what Julia was saying, right? This would be interesting to talk to Julia about. I don't know a counterexample in the interior, but it might exist, right? The objective function here is non-differentiable, so that makes it a little bit inconvenient. That's really the reason that you don't want to deal with this directly. And the functional is also non-differentiable, right? And this gets back to the problem of how do you correct it. We have the same problem in DFT, which is we're trying to somehow fit something that's non-differentiable to a practical form. And this is not a pleasant game to play, right? So the function has nasty properties, and you're trying to figure out a way to fit it, right? So if it wasn't that we're desperate in this field, this would be enough for us to give up. But we're desperate, so we have to keep going, right? Right? So because its objective function is non-differentiable, if I want to do anything practical, I have to fix that somehow, right? And I'm going to tell you a couple ways that we fixed it, right? The first thing we did is we said, well, why don't we just, instead of using the ground state energy, we're just going to thermally average our energies. So think of this as the microcanonical ensemble. In fact, it is the microcanonical ensemble, right? So we just thermally average the energies. This is exactly the same thing as we were doing here, but now we just inserted a little temperature, if you like. Now, of course, it's microcanonical. You can choose any weight functions you want, and so I just wrote it. But in our calculations, we always just put in temperature, right? Oops. Right, and the only requirement is that in some limit, you go back down to the function you care about, right? So you just smoothed it out. The only thing I can say about this is I don't know a nice way of writing a primal. I know an unnice way of writing the primal. I don't know a nice way of writing the primal for this. I'd be curious if someone here might just look at it and goes, oh, this is the primal in a pretty form. But I certainly don't know it. This goes back to, Dario and Augusto and Lorenzo. And this is a trick. This is exactly the same thing, but now we've added on the entropy, right? And this in fact is a better way of putting in temperature, right? This is the way you would put in temperature as a good statistical mechanic, right? And so if this is my functional, now I need to try to write the dual. Again, I'm running off the slide, but we'll see. You have the Lagrangian, right? And then we just do the standard tricks, right? We take our Lagrangian, we take its derivative set equals to 0. This gives us a nice expression for the log, which you can just, in your head, you can plug that in and you'll realize a bunch of stuff cancels out, right? And that's what you have to do, right? You have to get rid of your gammas, so you substitute in for them. We choose to put on the normalization because it gives us much nicer numerics. Lorenzo and Natalia didn't do it, and that's fine as long as you're just doing it with math. But if you're doing it numerically, you want the normalization in there, right? And so the normalization here, I think it'll show up on the next slide. But basically, you just take the trace of gamma, and it has a mu in it, and that gives you enough constraint to solve for mu. So you solve for mu exactly, you substitute it in, you substitute this in, and you end up with this expression, right? So this is the expression we have to do. All of us who are sort of statistical mechanics look like this and go, ooh, it's a partition function. We're happy with this, right? This is a form that we know how to deal with. If you think about it from the standpoint of what is the dual problem, if you start thinking about, okay, well, a log of an exponential, this tau cancels out this tau, this is going to go back to exactly the same thing that we had before, E minus trace of H gamma in the limit as the temperature goes to 0. So you sort of almost with your brain can see that this goes to the right limit.
Sorry.
Yep.
Is this?
Yes. Well, no, because it's just a normalization on the one matrix. So I probably should have called it lambda. So if we did it grand canonical, right, then we would add on a constraint on the particle number. This isn't a constraint on the particle number. It's just a constraint that the density matrix is normalized, right? So I've been sloppy here, right? When I did this, I didn't say, oh, and by the way, this thing has to have trace 1, and it has to be positive semi-definite and all of this. And part of it is, as long as the little gamma has the right normalization, the big gamma also has to, right? So it sort of all follows from that. And the other is that once I get to this point, then the positive definiteness will come out automatically. And in fact, even the trace 1 would come out automatically, right? But it's better for me to enforce it analytically, given that I can, right? Yep.
I have a question. In Lorenzo's talk, the gamma, the H somehow went into the exponential, and here it's somehow separate.
There's an H in the exponential.
Yeah.
right? There's also an H out, and that comes from the fact it's exactly the Lagrange multiplier on this constraint
Okay, thank you.
that's left over, right? So this wasn't zero, so it needed to be there, right?
You want to think about it? So here, what Lorenzo used is a big H. Here is the V with the plus sign.
Okay.
So,
Yeah, okay.
Yes,
Thank you.
Yeah, the H is the U and the V was my H.
Yeah, so yeah, because the U and V's are all our little h, right?
Okay, so they're still summed up before you take that.
Yeah, we summed them up. They're all the same. And then remember, this notation just says, make a copy on every copy of my subspace, right? That's what that notation means, right? Now, this is a little bit non-standard, but remember there's an arbitrariness in shifting by a constant, right? So I can just add this, and this will mean my optimum will have trace of h equals 0, right? So it's just a little penalty factor, just so I don't have to deal with degenerate maximum, just numerically, right? And the beauty of this is that, I mean, this factor is just from the penalty factor. This corrects my normalization, just forces my update on H to always have trace 0. This is just the average H from my ensemble minus, I mean, the average density matrix on the ensemble minus the density matrix I'm targeting, right? I'm trying to force the average of my guess to be equal to the thing I want, right? And that's, of course, it'll be 0 at the optimum, right? I've already here chosen to use the basis of the eigenbasis of this effective Hamiltonian, right? This is exactly an effective Hamiltonian, just like the form we do. So we do it in the eigenbasis. It's not practical otherwise. And in fact, because it's not practical otherwise, it really restricts what you can do in this theory, right? So you have to be such that you can somehow deal with this expression. Yep.
what do you denote by gamma k of H?
Gamma k, that's the one electron density matrix for this eigenstate, right? So when I solve this, there's some eigenenergy. It depends on what I chose for H, right? And there's a one matrix for this eigenstate, right? That's the density matrix of this. That just comes from the fact that the derivative of E with respect to H is gamma. Right? So I have now an objective function. I have a derivative, right? So now I can do math, right? And I took the opportunity to give 2 quotes from legends in the density matrix field, right? If you didn't know, you would probably guess wrong which was the mathematician and which was the chemist, right? This is the mathematician and this is the chemist, right? So here's boron 2 plus, right? It's a relatively evil system, and I just chose it basically because I can show that we're getting things correct, right? So here's the functional. The functional is actually discontinuous with respect to bond length. It's not discontinuous with respect to gamma. It's discontinuous with respect to bond length, right? And this is one of the reasons that it can be hard to do this sort of thing in these functionals. Of course, this is exact, right? We're solving this exactly, so everything works. It's been misformatted. This is just showing how this converges. I've taken the log of my penalty factor. This is the value of my functional, again, also on a log scale. I'm just converging it so that I can extrapolate down to what I care about, right, which is log of tau goes to minus infinity. It's linear, which means convergence is like 1 over tau. And what you'll notice is when I did this extrapolation, I got 7 places past the decimal, so like 9 digits of precision, which is enough, right? So this works, right? These calculations are not trivial because you have to evaluate the low energy eigenspace of this Hamiltonian, right? But it's doable. I would say it's easier than the corresponding calculation in DFT, right? So this is definitely doable. We've got some results we're doing for things that have, 5 atoms, something like this in it.
Why not? So you don't need full spectrum.
Yeah, you don't need a full spectrum because this is a temperature factor. It damps it out, right? So this is one reason that, you have a restriction on like the things that like Natalia and Lorenzo were talking about in terms of the types of functionals you could use. Like you can use all sorts of regularization, but if it doesn't damp you out fast,
So
you have a problem.
A threshold for the.
Yeah, so we put
spectrum, and
a
then it stops.
threshold on the spectrum, right? And I mean, in practice, in the code, you do something a little bit more sophisticated. You have to double check that you've got enough states, right? Right? Okay. So now I'm in position to try to say something. I can talk to you about extinctions and talk to you about questions, right? So my questions are basically, is this thing continuous except maybe on the boundary? On the boundary, it's clearly not continuous. Maybe it's continuous inside. This goes back to something we were talking about. You know, when the supremum is a maximum, we would say it's ground state ensemble representable. There is some, for that Hamiltonian, there is a state that has that density matrix, right? And that's exactly the case where you have this unique subdifferential, right? Right? So in DFT, we believe that the ensemble V representable densities are dense. So every density we believe is infinitely close to coming from a Hamiltonian, right? Is that true here, or is it not true here? I have no idea, right? In DFT, we also believe the state of things that don't come from a Hamiltonian at all, so the non-ensemble V representative, we believe that's also dense. Is that also true here, or is it not true here? And these are questions that might well have very different answers in the finite basis set case and the infinite basis set case. They do in DFT, right? These are very different questions in DFT, right? The other thing is, okay, maybe the supremum is a maximum and the density matrix is actually a pure state of this system, right? So this would be the pure state H representability. And then how often is this true? How often do you get a pure state back, right? I don't think there's any theorems in DFT about this, but it seems like it's very often true in DFT. And it seems like it's very often not true in this theory, right?
Hi, sorry, can I ask a question?
Yep.
Is there any relation between these questions between DFT and 1RDM? Is there any obvious somehow, this is harder, this is easier, or one implies the others? No, right?
Not that I can.
Yeah.
I think you say, is there any obvious one? No. Is there something? Yeah, maybe, right? Because there is a relationship between them, right? But it's not obvious, right? So both your descriptor changed in your descriptor changed and its dual variable changed, right? And they changed also in terms of space. And in some sense, this is nicer, right? So in DFT, you had something that was L1-ish and its dual was L infinity-ish, and that's nasty. And here you have something that's in a Hilbert space and its dual is also in the same Hilbert space, and that's much nicer, right? So if anything, I would guess it's easier here, but it's not easier for me, so. And then just to say that this is our classic formula. We like to write this sort of, derivative of our energy with respect to our Hamiltonian, but this is only true for non-degenerate states. And that's the same as in DFT, right? That's a sort of a trivial result, right? Okay, so these are the extensions that we know about. So Augusto and I have worked on the generalization of this to higher order reduced density matrices. You can do that. It's a standard trick. The beauty of it is when you do this, the in-representability conditions get mapped into a functional. And so your functional does all the work of your in-representability conditions, which is wonderful and terrible at the same time, right? I mean, it's conservation of misery, right? Just choose how you want to be miserable. This theory doesn't care about bosons, fermions, whatever. And in fact, together with Natalia and other people, we're working on the boson case and like the nucleon case and other cases. So it doesn't really, the theory goes true. it's trivial to extend it to multi-marginals. It's trivial to extend it to the grand canonical ensemble. It's non-trivial to construct an adiabatic connection, to think of some reference state that you can map where the reference state is easy to solve, and to extend that to excited states, but we've, I think, pretty much figured that out at this stage. We've been trying to figure out the theory of this convergence, right? And I don't feel very solid about it. I can do something, but not enough to make myself happy yet, right? So it would be nice to have some theory of exactly how this is converging here as we turn off our regularization. Okay, with that, I am finished, I think more or less on time, and I'll be happy to answer questions.